So when we have a mechanism that has a fast initial step, that means that it's the second or third or whatever step that's the rate limiting step. The rate law predicted by that step is going to have reaction intermediates. And we can't know what the concentrations of those intermediates are. So those can't show up in our experimental rate law, the concentrations of the intermediates. And I answered the question by accident. Why can't it have concentrations of intermediates? Because we can't measure their concentrations. So how do we deal with that? Well, when the first step is fast enough, we may establish an equilibrium. So you get an equilibrium between the reactants and the products. What is true about the rate of the forward reaction and the rate of the reverse reaction at equilibrium? They're the same. The reaction is going in the same rate forward and reverse. So here's an example of a reaction that has a mechanism with a fast initial step. So we've got hydrogen reacting with nitrogen monoxide to make water and nitrogen gas. Here's our observed rate law. Here's the proposed mechanism. First, let's check and make sure that condition 1 is met. Do these add up to the overall reaction? Well, that's not too hard to do. So we look at the intermediates here. We've got N2O2 is being produced in this first step, and then it's getting used up in the second step. And so we can cross those guys off. And what else we have going on here? We've got this N2O on both sides, and so those cancel out. Those are intermediates, or that is an intermediate. And now, if we add all the rest of these things up, we're going to get the same equation, because we've got 2 hydrogens and 2 NOs and 2 waters and 1 nitrogen. So these 3 steps do add up to the overall reaction. If they didn't, then we'd have to work on some other mechanism. So any questions?
Sorry.
It's okay.
So pretty much if they're on the opposite sides, that's when you would kind of cancel it.
Right. So you can think of it a little bit like adding math equations, where if you've got an A on the left side of one and an A on the right side of the other, they cancel each other out. Because what's happening is the N2O2 is being made, and then in the next step, it's being used up. So it was there, but we don't see any real evidence of it. Question over here?
Yeah, you answered it.
Okay, awesome. I answered the question before it was asked. Any other questions?
So if it doesn't cancel out, it doesn't match up, then it's just not.
Yeah, so if this doesn't cancel out, like if we ended up, maybe there was 2 N2Os here and we could only cancel one of them and we couldn't wiggle it around, then that can't be a possible mechanism because it's not going to give us the same overall reaction. I don't know what it's doing. I have no idea what it's doing. Okay, that's where we were. This is where I want to be. Okay, condition 2. The rate law predicted by the mechanism is consistent with the observed rate law. So here is the mechanism. This is an initial fast step. This is the slow step. I left the third step off because it was fast as well, and it doesn't really come into this. So we're going to look at the equation of the slow step, and that's going to allow us to predict a rate law for that. So what would the rate law there be? Rate equals a constant times the concentration of this. There's no exponent because there's no coefficient. Times the concentration of this. And again, the coefficient's 1, and so then the exponent's 1. So that is the rate law predicted by the rate limiting step in the mechanism. But this does not match up with the observed rate law because the observed rate law does not have the concentration of this intermediate in it. So what do? We need to somehow relate the concentration of this to other reactants, the original reactants. So this is an equilibrium. And so we have a forward rate constant. I'm going to call it Kf for K forward, and we have a reverse rate constant, Kb. The rates are equal. The forward rate equals the reverse rate because it's at equilibrium. So we could write a rate law for the forward reaction. The forward rate is going to equal a constant times the reactant for the forward reaction. So the concentration of NO, there's a coefficient of 2 on it, so this is going to be squared. That rate constant I'm calling Kf. Your book calls them like +1 and -1. The forward and reverse rate constants here. So what about this reverse reaction? The rate for the reverse reaction, we can write a rate law for that as well. That would be the rate constant for the reverse reaction times what? The concentration of the N2O2. No exponent because there's no coefficient. Everybody okay with that? Yeah. KR, oh, it should be KB. Back and reverse, yeah. Thank you for pointing that out. We'll just extend that a little bit and make it into a B. So the rate of the back reaction is equal to the rate constant for the back reaction times the concentration of the reactants for that backwards reaction. Okay? This is an equilibrium, so these rates are equal. If the rates are equal, then this side of these equations must be equal to each other. So we can say that Kf times the concentration of NO squared is equal to Kb times the concentration of N2O2. So we can rearrange this equation, and we're going to solve for the concentration of N2O2 because we want to get that out of that rate law. So the concentration of N2O2 is equal to the forward rate constant times that reactant concentration squared divided by the reverse rate constant. Be okay with that? I'm going to take this and plug it into the rate law predicted by the mechanism. So the rate predicted by the mechanism is a constant times the hydrogen concentration times the N2O2 concentration, which we have determined is equal to this. So this part in the big parentheses is this guy right here. So we can question.
Pretty much divide the KB.
Yeah, so I took this equation and I divided both sides by KB and just flipped it around. So this is equal to KFNO squared divided by KB. And then we're going to take this and plug it into this equation instead of N2O2. It doesn't matter which reactant you put before, because multiplying the order doesn't matter. So this is kind of a mess. Let's put all these constants together. So this is equal to our first rate constant and the forward rate constant and the backwards rate constant times the hydrogen concentration and the nitrogen monoxide concentration squared. All of these constants are constants, and so we don't really need to distinguish between them. We can just say, well, it's a constant. Well, maybe I'll call this K prime, just so that you don't think I'm like making something disappear. It's a different constant. So I am just doing algebra. That's all I'm doing. Yes?
For those K's, you said all those K's will be equal to the same number, like all three of them right there?
No, these three Ks are most certainly all different numbers.
Oh, okay,
Yeah, they're different numbers. Do we care what they are? No, we don't. Yeah.
Will KF and KB be the same though, for the equilibrium?
No, because of the stoichiometry here.
Oh.
Yeah. So I'm just taking all of those constants and lumping them together and calling them a different constant. Now, does this rate equals a constant times H2 times NO squared, does that look like the observed rate law? Let's go back and see. Why, yes it does. Imagine that. The looks on your faces are just priceless.
So it doesn't matter the values of those constants? Because when you think that right, that's in parentheses, you know the values of the
Right.
concentration.
Yeah, so what about all the Ks? It seems like I'm playing fast and loose with all those constants, right? So this forward rate constant has a value, the reverse rate constant has a value. Do we care about either of them? No, because this is just a fast reaction that's happening in a series of other reactions, and we really don't care what those numbers are. They do have values. We're just not going to try to figure out what they are. This constant, we can't really figure that one out easily. I mean, we could if we really worked at it, but we can't figure it out easily because we don't know what this concentration is. Right? We predict this rate law because of this elementary step. These are the two molecules that are actually colliding and reacting with each other. But we're going to take this concentration that we can't measure and try to express it in terms of a concentration that we can measure. And we do that by recognizing that we've got this equilibrium that's established. Now that equilibrium could lie very far to the right. We're not saying anything about the position of the equilibrium. It doesn't matter, it's an equilibrium, and so the forward rate is equal to the reverse rate, and so that gives us a relationship between these two concentrations. Two questions in the back.
Are H2 and N2O2 both intermediates?
H2 is one of the actual reactants. N2O2 is an intermediate, and so it's formed and then disappears again. And that's why we can't measure it. Question in the back.
The constant, so starting out from pressure, so it's like x times
Yeah. So we're taking a bunch of numbers. They're all constant at a given temperature for this reaction, and we don't really care the value of them. So we just lump them all together into one constant. That one constant we can determine because this is our observed rate law. The rate of the overall reaction is equal to a rate constant times these concentrations. This rate constant we can determine, and that's one that we may care about. Yes?
Are you going to do an example of this with numbers?
Am I going to do an example of this with numbers? I can't remember what's on the next slide, so I don't know. We'll have to wait and see and be surprised together. I write these slides and I go through them and I'm like, okay, I know what this is, but then I don't remember what's coming next, and so it makes lecturing a little more interesting when you don't know what's going to show up on the screen. Sometimes it's very surprising. This concept, though, is more important without the numbers. Being able to do this, to come up with the rate law and evaluate a mechanism, it's actually more important to know how to do it without the numbers. Any other questions? Okay, so here's an example. It doesn't look like this one has numbers, though. Sorry, Clarence. Okay, so ozone naturally decomposes to oxygen by this reaction. The experimentally determined rate law for the reaction is given here. This one's a little weird. Here, the exponent on that one is -1. We haven't seen anything like that before. Show that this proposed mechanism is consistent with the experimentally observed rate law. So here's our proposed mechanism. So two conditions have to be met. These equations have to add up to the overall equation, reaction, and then we have to be able to evaluate the rate law predicted by the slow step, and can we get that to match up with the experimentally determined rate law? So first thing, do they add up? What do I do? So here we've got ozone over here, and we've got O2 and oxygen, and then we've got ozone reacting with oxygen atoms. So this oxygen atom that gets produced here is going to get used up there, so we can cross that guy off. And those are the only things we can cancel out. So on the left side of the arrows, we have 2 ozone molecules. And on the right side, we have 2 oxygen molecules, plus another one is 3 oxygen. So these are correctly describing the overall reaction. So that's good. What is the rate law predicted by this mechanism? Which of those 2 steps are we looking at? The fast one or the slow one? The slow one. The slow one is going to limit everything. So we're going to look at this slow step, and we can predict, because it's an elementary step, we can predict what the rate law is. So the rate law for that is the rate is equal to a constant times what? Concentration of O3 Well, we're just looking at this one here. It's not the concentration of O3 squared. So, yeah, O2 squared. So let's try to make this clear. So this is what we're looking at. So we have ozone, O3, and then we've got O. And neither of them has a coefficient, so those are going to be first order. I got the wrong green. Everybody okay with that?
But why does it have a, because it has a 2 as a coefficient in the slow reaction for O2?
Well, O2 has a coefficient, but that's a product.
Oh, okay, so we're only looking at.
We only look at the reactants. Yeah. So we're only looking at the reactants. For elementary steps, we predict the rate law as looking at the concentrations of each reactant multiplied by each other, and they are raised to a power equal to their coefficient. Okay? Yeah.
So it doesn't matter if the intermediates get canceled out, you still use them in the slow reaction for the reaction?
Yes, that's a good point. So we did this and we canceled the intermediates out to look at the overall reaction. But that doesn't mean that those are canceled out and don't actually participate in those reactions. They do. It's formed in this first reaction, which is fast, and then it's used up in the second reaction. But the concentration of this is going to affect that second slow reaction, and that's the one that affects the overall rate. Any other questions? You're okay with how I got this? This is the rate law predicted by the mechanism. I'm predicting it from the slow step. Okay? We want to know, is this consistent with that? Well, are they the same? No, they're not. The problem with this one is we've got the concentration of an intermediate, so that's just not going to work. So we're going to do what we did with the previous example. We're going to look at this first step that's fast and say, well, this is most likely going to establish an equilibrium. And so then the rate of the forward reaction is equal to the rate of the reverse reaction. And this is an elementary step. We can predict the rate laws for it based on the chemical equation. So the forward rate is equal to the reverse rate. So the forward rate equals, what's its rate law? Kf, the forward rate constant, times just the ozone. Because it's one ozone molecule doing this, falling apart basically. The reverse reaction, I'll stay with B. I think the original B should have been an R, but we don't want to be more confusing than we have to be. The reverse reaction remember that guy is there. It's a constant for that reverse times O2 and O. Those don't have coefficients either. So, well, they have coefficients of 1, and they'll have exponents of 1. And chemists don't like to write the number 1 unless we have to. So these rates are equal, so Kf times O3 equals this. Kb times O2 times O. Because the forward rate equals the back rate. So KfO3 equals KbO2 times O. Following? So I'm going to take this equation right here, and I'm going to solve for O. Because that's the problem in the rate law predicted by the mechanism, is it's got the concentration of an intermediate. So I'm going to take this. O is going to equal this side divided by Kb and divided by O2. So it's the forward divided by the back and the O2. So I took these two guys, I divided both sides of this equation here. And I get this. O is equal to this mess. Now I'm going to take the mess and substitute it in for the O. So rate equals K times O3, and then this is where I'm inserting this little equation that I came up with. Okay? I'm going to consolidate all of those constants into a new constant. So the rate equals this new constant, and then I've got the concentration of O3 and the concentration of O3. So that's going to be the concentration of O3 squared, and then it's divided by the concentration of O2. So I could write that down here, or that's K prime O3 squared, and O2, oops, I don't know how I did that, O2 to the negative 1, which matches the experimentally determined rate law. Yeah. K prime is where I lump K, KF, and KB together. I'm giving it a prime because it's not equal to any one of them.
Can you explain how you did that? How you got that second to last one to the K equals K1 over here?
From here to here?
Yeah.
Okay, so what I did is I took this and this. And so that's K times K forward divided by K back. And that's a mess. So I'm going to give it a new name. I'm going to call it K prime.
Okay.
So I just pulled all the K's out.
Okay.
Yeah, okay. So then we have O3 times itself. So that's where we get this exponent of 2. So that's squared. And it's divided by this. The way this one's expressed, we use a negative exponent to indicate that it's divided by that. I love that you guys are asking questions, because otherwise it's going to be a blur. Yeah.
As far as like notation, is there any problem writing it initially like the first, where you had the first?
Like this? Would there be a problem writing that one like this? No. This is easier to type into the computer because you don't have to use an equation editor. So sometimes that's why it's written that way. It's just practical. They mean exactly the same thing. And if you're writing it out by hand, I would not have any preference for this one over that one. I would say they're equivalent.
This is just more of a rehash, but the reason he ended up using the fast one is because the rate of the second one did equal to the rate they gave you.
Well, the rate of the overall reaction is going to be equal to the rate of the slow reaction. So this rate is equal to this rate. But we need to know if the mechanism is correctly describing the dependence on the reactants. So we're looking at the rate law predicted by the second, the slow step. Right? So we've got this concentration times a constant. But we can't really say, just looking at it, that this is the same as that, because it's got different stuff in it. It's not the same. So this can only be a good mechanism if we can do this business and show that it is equal to the observed rate law.
Why do you have to use the fast reaction?
Why do we use the fast reaction here? Because we need some way to express the concentration of the intermediate. So this is working for a mechanism in which the first step is fast. If the first step is slow, you don't have to do any of this. The rate law should just match up with the predicted rate law of the first step. But when the first step is fast, it kind of messes things up. Okay, so let's do this. So let's make something up. So A plus 2B goes to C, and C goes to D plus F. This is the slow step, and this is my fast step. So overall, that reaction is A plus 2B goes to D plus F. Okay? The rate law predicted by this mechanism is the rate law predicted for the slow step. So that's going to equal a constant times the concentration of A times the concentration of B squared. So this predicted rate law from the mechanism has the concentrations of the actual reactants. Those we can measure. So this is what the mechanism predicts. If that matches up with the observed rate law, then the mechanism could possibly be correct. We don't need to do any substituting or rearranging or anything because these are the actual reactants. Does that help?
The order of those steps.
The order of the steps is important.
So if you have fast, slow, fast, and you're trying to get your slow step to match up with your observed, you use the first fast step, not the third.
Correct. So let me say that so people can okay, I'm lost somewhere. So in this example that we were doing, we had 3 steps. The first was fast, the second was slow, the third was fast. We don't need to look at that last fast step at all. Because once this occurs, the rest of it goes. It's going to go as fast as it can. Because it's this step that holds everything up.
Are we always going to be supplied with the fast and the slow? Or are we going to defer that?
That's a good question. Would you be told which one is fast and which one was slow? It sort of depends on the question. Now, if they said, here's the rate, the observed rate law, this is the correct mechanism, then you should be able to figure out which is the slow one. Is it going to be super straightforward? Not necessarily. But you could do it. So with this one, the second step being slow, then the rate law predicted by the mechanism involves this intermediate. We can't measure the concentration of the intermediate. And so that's why we have to assume that that first step is setting up an equilibrium so that we can express the concentration of that intermediate in terms of the concentration of an actual reactant that's measurable. Any other questions? So here's another one. Predict the overall reaction and rate law that results from the following 2-step mechanism. Wow, I'm glad I didn't accidentally make that one up. So overall reaction, what's the overall reaction? What do? Add the 2 steps together. Get rid of the red. So we've got this intermediate here, A2 is being formed, but then it's being destroyed. So we can cross that out. So the overall reaction is 2 molecules of A plus 1 molecule of B is forming a molecule of A2B. So there's the overall reaction. We're also supposed to predict the rate law. Do we look at the slow step or the fast one? We're going to look at the slow one. So I'm going to erase these because those are sometimes confusing. So we're going to look at that slow step, and what's the rate law that we predict from that slow step? A constant times the concentration of the reactant squared. It's squared because the coefficient is 2. I'm only putting, for each step, I'm only doing reactants. The products don't show up in here. Okay? Do I have to mess around with this like we did in the last one? No, because this is the reactant here, right? We can know this concentration. Now, does this rate depend on the concentration of B? No. So this reaction is zero order with respect to B. The concentration of B doesn't matter. It depends on the concentration of A, and it's second order with respect to A. But it's zero order with respect to B. Concentration of B doesn't matter. The rate will be the same regardless. Any questions? Yeah.
It's not always going to be like that though, right? For like D, are you saying doesn't matter for this, or is it always going to be?
It's not necessarily going to be like that. If the slow step had B in it, then the rate would depend on B. But the rate is not depending on B because the slow step doesn't even involve B. So this slow step is involving, say, 2 atoms of A coming together to form a diatomic molecule. That's the slow thing. Once that happens, it reacts with B and forms the product just really quickly. But it's the first initial getting those two together for this particular made-up example.
So just to be clear, if we're doing the opposite and we don't know slow and fast, and we're given that rate, we would know that because that first reaction doesn't have B, and the rate law doesn't have no concentration of B, then we would know that the first reaction is the slow.
Yeah. So if you weren't told which one was slow or fast, if it was asking you which is the slow step, and they said, they said this is the observed rate law, which of the steps is slow? Well, look at each of the steps, write out the predicted rate law for that. If the first one is slow, it'll just match up with the determined rate law. If it doesn't match up, and there's only 2 steps, you could just take a guess and say, well, it's got to be the other one. But the question also might want you to show why it is. And so then you'd have to do stuff with that intermediate thing. This one has an intermediate of A2. So if this was the slow step, then the predicted rate law would be A2 times B times the constant, right? And that is not the same as this, and then you'd have to express A2 in terms of A, etc. Any questions? Yes?
The one that we have been doing with the steps,
Mm-hmm.
Even if it is a slow reaction first, you still follow, like, I know you obviously wouldn't have to do it, like, say if you did, would it still work out?
So I'm not quite understanding your question. Could you do all of that rearranging business on a later step that was fast and have it work out? Is that what you're asking?
I'm asking, like, so when the slow step is first, we don't have to rearrange anything.
Right.
It's fine. If, so say, like, if we don't know,
Mm-hmm.
is there, I don't know, I mean, like, if you accidentally did the extra work on one with the slow being fast, like slow being first, would it still work out, or would it just destroy the whole thing?
I think you'd find that there was not much to do.
Okay.
Yeah, I think it would kind of take care of itself. Yeah. Any other questions?